Welcome to chapter 5. In this chapter, we will discuss alternative approaches to the issue and commit stages. So, issue and commit stages, the way we have described in chapter 4, this has kind of been described in a very simplistic manner. So, a modern out of order processor is way more complicated than the basic description that has been provided in chapter 4. Nevertheless, the aim here is to basically look at some of the corner cases and then move on to a simpler design, which of course is less efficient, and then discuss. So I have the schedule over here, and so then we discuss. First we complicate our design, then we simplify it and discuss something which is less efficient, and finally we discuss compiler based techniques, where of course we discuss a different paradigm, where we discuss how to use software based techniques that include smart compilers and profilers to generate efficient code. So in this chapter we do require some background, and the background is of course chapter 4 on the issue, execute and commit stages. So we will start with out of order pipelines. This is something that is required for the background. Then of course we need to know the wake up select mechanism in great detail, and finally precise exceptions and instruction commit. So the requirements for this chapter are these three things, which you will get in chapter 4. So in chapter 5, the main thing that we look at is called aggressive speculation, where we complicate things. As you see this nice looking painting over here, even with 3 or 4 simple crayons, a complicated picture has been drawn. Something very similar will be done in hardware, where with our basic mechanisms. So what are the basic mechanisms? Well, if you think about it in hardware, we always joke that hardware essentially has a set of registers and a set of wires, that's it. So whatever we do is just with registers and wires and with nothing else. So with that we implemented a host of stuff. So the biggest attraction in that sense in the previous chapter, which was chapter 4, was branch prediction, which is one form of speculation, where if we detect that a branch has been mispredicted, we flush the pipeline, right? So we flush the pipeline, and when do we do that? We wait for the mispredicted branch to reach the head of the reorder buffer. At that point we detect it and we flush the pipeline. This is not the only form of speculation. We have other kinds of speculation as well, which we will discuss in this chapter. So these other kinds of speculation are low latency speculation and value speculation, which we will discuss in this lecture. So the idea here is simple. With low latency speculation, it is that we have different levels of memory. We have an L1 cache, L2 cache, main memory and so on. So we have a memory hierarchy basically. So the pipeline is connected to the uppermost level of memory, which is fast, which we have assumed to take 1 or 2 cycles. But that does not contain all the memory locations. So then we have an L2 cache, which contains a superset. So we can make a guess that we will find the value in the L1 cache. But if we don't find the value, we'll have to go to the L2, which takes more time. But from the point of view of the pipeline, when we do an early broadcast, we can, as we shall see in some cases, in many cases rather, we can make a guess that we will find the load in the L1 cache and proceed. But what if our guess is wrong? Well, we will see what needs to be done. Similarly, we can also predict values. So recall that for read after write dependencies, which were true dependencies, we have not done anything. We said that look, it's a read after write dependency. We have a producer, we have a consumer. The producer produces the value, the consumer consumes the value. We have nothing to do, right? That was our stand. But if we have a producing instruction over here, let's say IP, which produces something that the consumer instruction consumes, So if this is, let's say, a memory location or a register, we can have a value predictor if it is possible to predict the value. In this case, we can run the producer and consumer in parallel and the dependency is broken. Of course, if the value prediction is wrong, so in this case it's speculation, because we not only predict but we also move forward. So that is speculation. So if the speculation is wrong, then of course there is trouble, right? We need to do something. So what do we need to do? Well, we will see, but the problem at hand is that in an aggressive processor, we do a lot of guesswork. Based on that, we wake up our instructions and we execute them. Sometimes the guesswork turns out to be wrong, and in that case, we need to do something. That's the crux of our discussion. What are the types of aggressive speculation? Well, there are many types, but these are clearly the most common. One is address speculation, where we try to predict the address of a load and we dispatch the load early to the memory system such that all the instructions that are dependent on the load can be woken up. This is slightly more specific, where we predict the dependencies between loads and stores. That allows us to do many things. We can send loads early, we can forward data between stores and loads, bypassing unresolved stores. Next is latency speculation, where we assume that a given access will hit in the either in the load store queue or in the data cache. A hit means that we will get the value, right? So a memory access will take 1 cycle or 2 cycles. In the sense, we know the latency. Then we have value prediction, which of course is the hardest, but it is the only way of working around read after write dependencies. So there is no way of actually solving read after write dependencies, this problem. The only way that we can actually still get a high IPC in code that has such dependencies, if we somehow make the producer and the consumer instructions run in parallel. This is possible if, let's say, the value that the consumer instruction reads, that value is predicted, and on the basis of that we proceed. So this is known as a speculative execution, and modern processors do embody many kinds of speculation like this. But mind you, with any kind of speculation, there is a chance of a mistake. In that case, something needs to be done. So let's look at our address speculation. So we have seen this before. So this diagram over here, we had seen something very similar while we were predicting the outcome of branches. So the predictor is generic. So we had discussed this there also, that this is a generic structure of a predictor. So let's say for a given memory address, if we want to predict the address of the load or a store, we can use exactly the same structure, where we use the n least significant bits. We use it to access a table of 2 raised to the power n entries. Wherever there is a hit, if let's say there is a match over here, then there will be an address over here, and this we will use as the load address. Can be the store address as well, but since loads are on the critical path, we typically do the prediction for loads. So this is a very simple scheme where you predict the last address, right? And unlike branch predictors, we cannot use saturated counters over here, because this problem is not amenable to saturated counters, right? So it's not fundamentally a counting problem. We are storing an address, so in this case we store the last address. So as we had discussed, the branch predictor gives the generic structure of a predictor, which of course can be used in many different cases, scenarios. So let us now look at a different kind of predictor called a stride based address predictor. So in this case, let's take a look at the C code first. The C code is doing something that is rather simple. The C code is just taking an array of 10 elements and adding all the 10 elements and producing a sum. So what we have over here is that we have sum plus equal to array I, where I is varying from 0 to 9. So we are adding the first 10 elements. So that's what we are getting, the sum of the first So if I were to do it in assembly, I can convert it to simple disk assembly where I map I to 0, sum to R2. I map I to R1, sum to R2, and the base address of the array R is stored in R0. So what I do is that I compare R1 with 10 every cycle. If the comparison fails, if there is no equality, if there is inequality, then I load the value of the base of the array to R3, and then I update the sum over here, and then what I do is I increment the memory address, which is the base address of the array over here. I increment the loop index and then I jump back over here. So this line is what I want to draw your attention to first. In this case, we increment the base address by 4. Why by 4? Because we are assuming that the size of an integer is 4 bytes. So that's why we are incrementing it by 4. Now let us consider this load instruction, which is the most important. So it's so important that I'm erasing the ink on the slide. Whenever I do that, it should be very important. So here what I'm doing is that I am loading a value from the address stored in register R0. This line should be read along with this line where we are incrementing the value of R0 by 4. So the address stored over here is getting incremented by 4 every iteration. So we can think of this as a stride based pattern where if I have an address predictor over here, then the address predictor will have to explicitly take into account the fact that every time we access this instruction, the address is getting incremented by 4, right? And 4 in this case is the stride. So what do? Well, we use a different stride based predictor because in this case, the last address based predictor will not be useful. So we need to use a different kind of predictor called a stride based predictor. So the last address, let it be A, right? Let the stride be S and the pattern be P. So what we have is that we have a similar table as over here, which of course is addressed with the n LSB bits of the program counter. Each entry looks like this, where we have the address, the stride and the pattern. So in each entry, what we store is the memory address computed the last time. Along with that, I think something has gone wrong. Okay, yeah. Along with the memory address computed the last time, this instruction with this PC was executed, we store 2 additional pieces of information. So we store what is the stride, which means historically what the memory address has been getting incremented with and whether we follow a stride based pattern or not. So let's say for the sake of prediction, right, if let's say the pattern bit is 1, which means that we can conclude that we follow a stride based addressing pattern, we can predict A plus S as the next address. When we actually compute the address of this load instruction, so let's say the computed address is A dash, so we subtract A dash minus A and we equate that with the stride. So I should use a double equal to because it is clear it's an equality and not an assignment. So we pretty much equate that A dash minus A and see if it's equal to the stride. So if a stride based addressing pattern is indeed being followed, this will be equal to the stride. So we update the last address from A, we update it to A dash. The stride of course remains the same and the pattern bit is set to 1 if it is not already 1. Alright. But let us say that a stride based addressing is not being followed, then we have a choice. So if this is the 1 bit, from 1 we can convert it to 0, or this can also be a saturating counter. So it is important to understand that a saturating counter is a generic mechanism which is not just limited to branches, right? Clearly not. So for example, if I were to consider the code that is shown here in slide number 7, again I want to draw your attention, so I'm erasing the ink on the slide. So let us say that this was part of some high level function foo. We will find a stride based addressing pattern over here, right? So this is something that we will find. But after we exit the function and we come back again, right? So let's say we exit and a long time later again we come back, we will find that for the first access the stride based pattern will not hold. But that does not mean that the behavior has changed. This is essentially a temporary aberration. If we use a saturating counter, then what we can do is we can ignore that and we can still continue to predict on the basis that it is indeed stride based, and the rest of the predictions will turn out to be correct. So that is why whenever we store something about the past history, we should think not once but twice but thrice that what exactly is the pattern that is being followed and how much of hysteresis do we want to give it. If we want to tolerate these occasional anomalies, this should be a saturating counter. That's number one. And let's see if the stride changes, then we should see whether we should just treat it as an occasional anomaly and not change the stride. Or let's say if there is a persistent change in the stride, then of course the value of the stride S should be changed over here. Alright. So much of this depends on actual simulation and actual engineering. But the key idea is that we store these three pieces of information. And the prediction, if a stride based pattern is followed, is always A plus S. And whenever we resolve the address, we always compute A dash minus A, where A dash is the resolved address, and compare it with the stride. If it is equal, well, that's great. We can increase the confidence of P. If it is not equal, we can do several things. Much of that depends upon whether P is a saturating counter or not, and the amount of hysteresis that we want to give it, right? And so there is no hard and fast rule on how much of hysteresis needs to be given. So typically what happens is that we run hundreds, thousands of simulations on the programs that people are expected to use, and we look at the behavior that these programs are following. Alright, so we have discussed address speculation now. Let us now discuss the load store dependence speculation. So what has been seen is that if a given memory address, let's say it has a load, if there is a collision means a same memory address with a previous store in the pipeline, this tends to be in a sense a predictable steady state behavior, and these collisions in a certain sense can be predicted, which means that if I have a load, I can predict with a reasonably high accuracy that look, the value will actually come from a previous store that is there in the pipeline. In the sense, an LSQ forwarding will give the value and the value will not really come from the data cache. Why is this the case? Well, we will have to look at the nature of the code. So a lot of code is essentially this register spill code, right? Which leads to this behavior. That when we spill a register because we run out of registers and then we execute a function and restore it, in that case what happens is that we have a store and then we have a load, and as I said, we can either spill because we run out or we spill it because of a function call. Regardless of the reason, we always have the store load pairs, and since they are not that far apart, they will still be in the pipeline. So moment we see this load, we can say with high confidence that look, there is a previous store that will supply value to it. And there are many other examples of coding patterns, mainly with respect to function calls or with respect to loading data and so on, where such a pattern holds. So if you can predict these collisions with good enough accuracy, So let's say if we predict that there are no collisions, then we don't have to wait for unresolved stores. We just send the load directly to the cache, we get the value and we wake up the consumers. Or let's say if we predict that there is a very high probability of a collision between a store and a later load, even if there are unresolved stores in the middle, we need not wait for them. Because if we have predicted that look, this store and this load are going to collide and nobody else, then we directly forward the value, don't wait for these, and the load proceeds. So this of course is highly dependent upon the way that we write programs, but given that most assembly programs are written roughly in a similar manner, and this pattern holds across languages, across compilers, across processors, that is why processor design should be designed in such a way to leverage this pattern. So there is an important philosophical insight over here. Almost all architectural optimizations are in a sense based on, they are learning based optimizations, right? So they look at the way that programmers actually write their code, and on the basis of that they decide what kind of hardware will best take advantage of these patterns. If there were no patterns, no architectural optimization would actually work. Okay, so how do we find collisions? Nothing. We have a standard template that we have set up in our good old branch prediction days. So given that we have learned that, we just keep on using it. So some loads do show a consistent behavior. They can be predicted as colliding or non-colliding. So a little bit of idea, whenever you have these bulbs, that is when we have our insight. So we have a collision history table CHT, which takes an n-bit PC, n-bit program counter. And then, well, it points to an entry, same as a branch predictor. We predict whether it's colliding or non-colliding. And here you can have a single bit or you can have a saturating counter. No problem at all. Right? So we can have a saturating counter which can take care of those occasional anomalies. How many bits to have? Well, a lot of those are outcomes, outcrops of a simulation related study. Let us now discuss how to use the CHT. So the CHT is used like this, that we can use it at 2 points. We can do the prediction itself at 2 points. The first is at the time of decoding, which of course I am not showing over here. It's not, can be done. Also, it can be done at the time that we resolve the address of the load. So it can be done at 2 points. So I am showing here that when we compute the address of a load, we access the CHT. So this is of course at the time of resolution, but also it can be done at the time of decoding. So in this case it doesn't matter, but we will show other cases where it actually does. So if the load is predicted to be colliding, what it basically means is that in the load store queue there is a store which has the same address with the load. So it doesn't mean that there are no intervening stores in the middle that don't have the same address, but there is at least one. So what do we need to do? Well, we need to wait for all the prior stores in the load store queue to be resolved, to get resolved. Once they get resolved, what needs to be done is two things. Either we get this forwarded value, that is option 1, well then there is no problem at all, or we send the value to the data cache. If it is predicted to be non-colliding, which means that there is no forwarding that is going to happen, most likely of course, then we send the load directly to the data cache and we are done. Alright. Once the address is resolved, so basically the address of, let's say, the store in consideration is resolved. So if you don't know which one, then pretty much once the addresses of all the stores before the load are resolved, right, and let's say all of them, it's known, the entire state of the load store queue before the load is known, right, the store queue actually, not the LS queue, but the store queue before the load is known, we are in a position to see whether there is a collision or not, right. So if any of these addresses match, then there is a collision, else not. So in this case, we update the CHT with this information. And let's say that there was a collision, but we speculated past it. There is a need to recover the state. As simple as that. So this essentially allows us to send some loads which are non-colliding to the data cache, L1 cache, without waiting for unresolved stores before it to get resolved. So that wait time we avoid. So which means we can send loads early, we can wake up their consumers. So this gives us more IPC, right? It gives us more parallelism and more IPC. This can be augmented with more information, which is where when we predict becomes important. So let's say that we do this prediction at decode time. So what we can augment it with is, we can augment it with the store to load distance, which basically means that if there is a forwarding, how many entries separate the store and the load, right? Howsoever it is measured, because we have separate load and store queues. So it can be the number of stores before it, number of loads before it, or a sum. It doesn't matter. For a load, it will typically be the number of stores before it. So which will basically essentially be this distance, where these are all stores. So if this distance is d, what we do is that a load waits till there are less than d entries before it in the LS queue. So of course this needs to be interpreted contextually. So in the context of this description, it is the number of entries before it in the store queue. So the load basically just waits till the number of entries in the store queue are till they are less than d, which means until they are greater than or equal to d, nothing, but the moment it goes below d and no forwarding has happened, you are kind of sure that no more forwarding will happen, because this is what we have predicted. So load at this point can be dispatched to the data cache, right? It can be sent to the data cache, because what we predicted is that we predicted a collision, but we predicted something more also. What we predicted is that the store to load distance can be measured in different ways, but let's measure it for the time being with the number of stores before the load. So this was predicted as d, and the moment that the distance between the load and the earliest store in the store queue, right, this falls below d, we will find that this prediction pretty much doesn't hold, which means that there is no more matching stores, right? There are no matching stores, most likely, of course. So then the load can directly be sent to the data cache. So this is an optimization, no doubt. It uses more information, which is the distance d. Whenever we use more information, we use more space. So we expect a better prediction, a more accurate prediction, a more informative prediction. In this case, the prediction indeed gives us more information, and this information can be used productively. Now let's come to another idea, which is one of the most sophisticated ideas in this space. So this is a far more refined proposal, so to speak. So as compared to the basic CHT, this mechanism is known as store sets. So we start out in the same manner. So always our predictors will keep on looking the same, right, pretty much our basic branch predictor design. So here our explicit aim is to remember load store dependencies, and pretty much for a load we should be able to say that which stores are kind of part of what is its store set. But a store set is basically the set of all the stores that can forward their value to a load, right, pretty much like that. Store set is a set of stores. So here is what we do. So I will describe this kind of part by part, because it's a kind of an intricate scheme, but once understood, it will not appear to be that complicated. So given a load or store, we start in a conventional manner where we extract the n least significant bits. We use it to access a 2 to the power n entry table. So this table previously was giving us direct prediction information. In this case, it will not give us. It will instead give us a pointer to one more table. So what is the first table? The first table is the store set identifier table, SSIT. What we read over here is for a load or store, we read its store set ID. So for every load in the simple design, we'll have one store set that is associated with it, and that will have a unique ID. So we will discuss slightly later how that unique ID is given, but let's assume it has a unique ID. So then we will figure out this by reading this table. Similarly, every store, it is part of one store set. So this, of course, in the initial proposal, it was one store set. Later on, it was extended to multiple store sets. But in this slide set, we are only discussing the simple idea, which is a single store set. So every store also, if you read, then you will have a pointer to its store set ID, which is essentially the store set that comprises, that doesn't comprise, but that contains this store. Alright. So what we do is we use the store set ID regardless of whether it's a load or store. We use it to access the LFST table, which is one more table. So if let's say this is a 7-bit ID, then this table will have 2 raised to the power 7 entries or 128 entries. Each entry stores the last fetched store in the store set. So as I said, a store set is basically a set of stores. And it will tell us that, look, a certain store which is there in the pipeline is the latest in this store set, which means it will most likely forward the value. So how do we identify an instruction? Well, we provide each instruction with a unique instruction number, which pretty much, if you read the book, it pretty much is a number which is twice the size of the reorder buffer. So it can be a circular counter, which can be, anything more than actually the size of the reorder buffer, depending upon how we are willing to construct it. Sorry, I stand corrected. So it's actually more than twice the size of the reorder buffer, such that if there is one instruction, before it or after it, you will never have the same instruction repeating, right? So it's more than twice the size. So then if we have a cyclic counter like that, we can generate a unique instruction number for every instruction in the pipeline, such that at one point of time, there should be no repetition. So basically, if let's say in the pipeline, all instructions can have a unique number. And furthermore, if there is one instruction over here, so it will first start at the bottom of the ROB and gradually work its way up the ROB. So in its lifetime, it should never see two instructions with the same number that are actually different. So having an instruction number that varies between, let's say, 0 and any number that is greater than twice the ROB size, this to a certain extent solves this. So the long and short of this story is that every instruction is allotted a unique instruction number. And in the LFST table, we say that, look, in this store set, what is the instruction number of the latest store that has been fetched? So this check, mind you, is done at decode time, not at resolution time. So the load basically knows that if I am the load, there are a lot of instructions that have been fetched before me. Out of these, some of these stores are in the store set. What is the store set? The set of all the stores that can potentially forward their value to the load. Out of this store is the latest. It's a part of my store set and it is the latest, which means this is the store that will most likely forward the value to me. The rest are important in the sense they are in my store set, but I don't care. I only care about the ID of the latest store because that is what is going to forward a value to me. And that to me is the one that I should be concerned about, and this is the last fetch store in the store set. And how do I identify it? Well, as I said, we have a scheme of providing a unique instruction number to each instruction, and this is recorded in LFST given the store set. So load basically reaches the LFST via a single level indirect, and it finds the latest store ID and it stores it. So every load basically, if of course it has a store set associated with it, has the ID of the latest fetched store LFST, which it will use. How will it use? Well, so this is kind of a loaded text heavy slide, but let's go slow. So what we have said is that for every load we have an associated store set. Stores that have forwarded values to it in the past are members of the store set. And a store in this case is a part of a single store set, but as I said, there are extensions to this idea where this rule is broken, but we are not considering that. So what do we do for loads and stores? Well, for loads and stores, of course, we do different things. The first is that we read the store set ID, right, which is exactly what I'm showing over here. This is step 1. The second is we get the instruction number of the latest store in the store set from the LFST. Of course, subject to the fact that it exists, which is step 2. The load waits for store S to get resolved. So the load basically locates the store S in the store queue, or we can say that in the store queue, whenever a load is resolved, it probes the store queue to find if a store with that instruction number is there. So let's say this is the load which got resolved. So once it does, it finds the actually this can be done before resolution also. The moment we enter a load, if we know the LFST, the latest store of the store set that this load is a part of, then the load can simply probe the store queue and find the entry in this, that is the latest fetch store, right? So then we can do several things. One is that if this has not been resolved, we wait for this to be resolved and we can check the addresses. The other is we don't have to check for the address. The moment we know what is to be stored, we can do a direct forwarding even before the address of the load has been computed, right? So several things are possible. But in all cases, we can ignore all the instructions between the store and the load, because with very high confidence we have predicted that there is a dependency between the store and load. So let me explain this once again, because this is a reasonably complex concept, so should be explained in different ways till you are able to understand it rather thoroughly. So the idea, if I were to explain it in a different way, would be that let us consider the conceptual view of the load store queue. So let us say that we add a load at this point at decode time, and at that point we read the SSIT and LFST, and we are sure that there is a store before it in the LSQ where we clearly have a store set based match. So what can be done in this case is that if we really want to aggressively speculate, when the value that will be stored, which is roughly also the time when it will get resolved, because let's look at a store. A store instruction will be, let's say, of this type, that store Rx, let's say some offset, let's say it is 8 RY. So what we will do is we will read Rx, we will read RY, both from the register file roughly at the same time, and then we will add 8 to RY, that will give us the address of the store, and we will write both the values, which is the resolved address as well as the value that needs to be stored at the same time. Why at the same time? Well, because if we do it at different times, that will unnecessarily increase the number of ports that we require in the LSQ. So in terms of implementation, it will be hard. So at the time of resolution, we will write both. See, the store has been resolved. Then we can directly take the forwarded data even before the load has been resolved and continue. So this will give us, in a sense, a certain speed up, and we don't have to wait for the load to be resolved. And this, as far as we are concerned, is a performance enhancing optimization. All right. So this is clearly a very powerful thing, because what we are doing is we are ignoring all the stores and loads. Well, loads can be ignored, but all the stores in between, and even if they are unresolved, we are saying that we don't care. For a store, what we do is we read the store set ID, and then when are we accessing the store? Again, let's say right after decode, we are accessing the SSID. So this store is clearly the latest instruction in the store set. So we update the LFST with the instruction number of the current store, and subsequently we can speculatively forward data to loads that are there in its store set. Well, I wouldn't say loads are there in the store set, but I would say that loads that are supplied value by stores in its store set. All right. And so this is how we can, in a sense, manage these fine-grained dependencies and also increase the ILP using this technique. When and where do we update the tables? Well, the details are there in the book in chapter 5. But clearly, when we detect a load store dependence, then if a store set has already been allotted, we simply add the store set, we simply add the load to the store set, or we just record that for this given load, this is the store set. And let's say if the store is not a part of the store set, then we add the store to the store set, right? We get rid of its previous mapping and we add it to the store set. And let's see if the store set itself is not there, then we create a new store set and we update the SSIT such that both this store and this load point to the same store set. So this bookkeeping is always done when we detect a dependence. We need to do this bookkeeping with the SSIT and LFST. But that said and done, this is clearly a very powerful optimization. It's clearly more effective than the CHT, because CHT just predicts a collision. In some cases, it can predict the collision and also have distance information. But again, that's not that accurate because the distance can vary. The code can vary, right? The behavior of the code can vary. But this is a far more accurate method of predicting which stores will collide with which loads. Then we can explicitly wait for those stores and forward values and so on. Alright, now let's come to the next, which is load latency speculation. So we do have a memory hierarchy. Much of this will be discussed in chapter 7. Hence, I really don't want to broach this topic right now. But all that I can say is that, look, we have a hierarchy of memories for performance reasons, of course. So there is an instruction cache which I am not showing, but I am not showing this. The instruction cache provides instructions to the pipeline. The data cache is fast. We have assumed a 1 to 2 cycles it takes to access. It has a very high hit rate of 90%. For all the accesses that go below, so this 50% is essentially a local hit rate, in the sense that if 100 requests come to the L2 cache, only 50% of those are satisfied. This is a far slower structure. It takes 10 to 50 cycles. And of course, if we don't find it in the L2 cache, we go to the main memory where we will find everything. Again, we'll break this assumption, but let's assume it holds for the time being, and this has a very long access time, 300 to 400 cycles, very long. So we don't know for sure where we will find the data for a given load, right? So we don't know. So that's the reason I buried my head in sand. But you can always make a guess, right? So we love making guesses. That is why we call this subchapter aggressive speculation, where we guess as much as we can in the hope of getting that last drop of ILP, right? It's like, searching for water in a desert. We guess, speculate as much as possible, such that whatever we can extract in terms of a slightly higher instruction level parallelism, we do that. So for load instructions, we predict if it will hit in the data cache or not. If it will, we do an early broadcast, right? And so let's say that if let's say we have a small predictor, says it will hit in the data cache, well, no problem. We broadcast, we wake up the consumers. If the prediction is wrong, we need to do something. We'll see that in the next section. We can design a hit miss predictor for a load. Given the load PC, we can say whether it will hit or miss. The idea is very similar to a branch predictor, so we will not discuss the same thing over and over again. Here also we can use simple bits or we can use saturating counters, right? So everything depends upon the nature of the workloads. So a lot of architectural simulation has to be done, but the basic pattern is the same, right? So you know this by now. What else can we predict? Well, it turns out we can predict values as well. So value prediction, as we have discussed, is the only way to break a read after write dependency between a producer and a consumer. The only way is if we can somehow predict the values that the consumer will use. And clearly one of the slowest instructions in this category, one of the biggest culprits in this category is the load instruction. Alright. So the load instructions value is something that we can predict. Alright. So why are values predictable? Well, many times we use, there is data redundancy, so we use the same values over and over again. Like let's say it's a scientific program, we use the values of E and pi over and over again. Bit masking, many a times, even if we are considering long values, we are only interested in a few bits. So if those bits in a sense are predictable, many times we are using constants in our code. Many times we have error checking code where we almost never have errors, but a large part of the code is the same. A lot of values that it uses is the same. Virtual functions, well, virtual function is an important, virtual functions are important things in C++. So what they basically say, right, so my aim is clearly not to introduce an object-oriented language here, but clearly some introduction might be due. That look, let's say I have a vehicle class, right? So it defines everything about a vehicle. And let's say in this you have get type. So vehicle will have a type. And then we have a subclass of vehicle, let's say cars. So cars will again have a definition for the get type function, but the get type for a car will be a car, but for a vehicle it might be undefined. So we can always have this. So this is the key of any object-oriented program, right? We can always have a pointer to a car, like let's say in a car star. So as is the convention, class starts with a proper, class starts with a capital letter and a variable with a small letter. So let's have a car. And let's say that we have initialized the properties of the car. So then we can have a pointer to a vehicle and set this equal to car, right? Now what do we do is that let's say we send this pointer v across a set of functions, right? Doesn't matter. So let's say we send this pointer far, far away, and then we call the get type function. So mind you, we are calling get type on a pointer to vehicle. But what will magically happen is that the car will also would have defined a get type function. What will magically happen is that instead of this function being called, actually this function of the car will be called, because this vehicle is actually a car. Even though in the entire code we are using vehicle star, but this function will get called, and this is a virtual function. And the way it actually does happen is that we have a small table with each object, which essentially says that look, for get type, it just has a pointer to the PC, and in this case it is this PC. So all of this code, right, for virtual functions is predictable. Similarly, register spilling, which we have already seen. So if we take a look at all of this, I would suggest the viewers to just take a look at this. These are all coding patterns, right? So for example, before object-oriented code came along, virtual functions were not there. But once that came along, And once, let's say, there was a big need for register spilling, hardware always has to take into account software patterns. And virtual functions are clearly a big example of that. That once programmers started writing programs in a certain manner, hardware had to take that into account. And then hardware had to be redesigned to, in a sense, ensure that C++ programs run quickly, right? So the market for C++ programs, which was not there in, let's say, the mid 80s, by the late 90s had become huge. In fact, even now, most of the proper software is written in C++ and other .NET languages, but C++ is still big, very big. So this is where hardware designers had to step up and ensure that their processors could actually run these programs quickly. And then they realized that virtual functions are a very important object-oriented programming concept, and this needs to be supported. One of the key ways of supporting virtual functions is, of course, having support for function pointers, right? That is one in hardware, which means that we need support for indirect branches where the target is not hardwired but it is stored in a register. So this is undoubtedly required. But other than that, they also realize that many of the values that are used here are predictable. So you need a value predictor. So value predictors pretty much follow the same pattern that we have been discussing up till now, which is either predict the last value, or let's say the value increases with a constant stride, predict it on the basis of a stride, or you do it on the basis of profiling. What is profiling? Well, profiling is like this, that we take the program, we give it a set of representative inputs, right? So you give it a set of dummy inputs or representative inputs, however you want to call it, and you have a lot of instructions that are embedded in your profile program, but they will not be a part of your final program, which will essentially write the results of values and write which direction the program is taking, write down the outcomes of branches, a host of information to a file, a regular file. So this file can then be analyzed, and then important pieces of this information can then be used to actually kind of pre-program the hardware such that, let's say, for example, you can say that, look, for this PC, it most often takes this value. So let's say if it's a load PC, it most often reads this value from the memory system. So all of this information will come via profiling, and all of this information in a certain sense can be fed to the hardware via special instructions, right? If the hardware has a value predictor and instructions have been exposed to software to program it, so in that sense you will see that your accuracy will improve substantially. So I would advise all the viewers to take a look at the program, GProf. What does GProf do? I'll not tell you now, but you take a look at it, you'll get to know what it does. So it is something on these lines along profiling, but what it does, you explore on your own. This is the last slide in this section where we discuss the use of confidence bits. So as you have seen, we have predicted a lot of things, but of course our prediction, should we predict all the time? Because many times, unlike branches where we are forced to predict, in many cases we need not predict. So we can have a separate confidence table which will predict the confidence in a sense that how strong will the prediction be, and this can use saturated counters. So we can say that certain things can be predicted with high confidence if historically they have been very predictable. Otherwise we say that they are low confidence. And then of course we'll have a predictor table. As we have seen, we enter the PC, we get the prediction. So we first use the confidence table to find out if it makes sense to predict. Simultaneously we also predict. The predictor table can use a single value, can use strides. We can have complicated predictor tables that use the last k values and try to predict on the basis of that. So these things can be arbitrarily complicated. But the question is that whether we should use the predicted value or not, we can use the separate confidence predictor to actually tell us. Alright? And this is an important augmentation to our prediction mechanisms, because we don't want to unnecessarily predict low confidence stuff and just lose cycles, right? That would be really bad. Once the results are available, we update both the confidence as well as the predictor table. And of course, if the results are available, we also know whether we made a mistake or not. So we recover with a replay flush mechanism. Next, we will discuss replay mechanisms where we show how we recover from these misprediction, mispeculation related faults.